I'm giving the talk for Zaman Kanji, who's the PI of this project. He has a personal commitment this week and so is unable to join us. But other people here at the meeting are Luis Ladino, who's another co-investigator from UNAM, and two postdocs, Kunfeng and Carolina, and a PhD student, Sebastian. So we're going to talk about Cirrus, or I'm going to talk about Cirrus cloud thinning. And this talk is this is a fully experimental project, so the first year or so has been spent bringing people into the project and building experiments up. So I don't have too many data to show you. This talk is a little bit of a follow-on from what Zaman presented back in November, but reintroducing that to some degree. So the idea is to, with Cirrus cloud thinning, is to inject heterogeneous ice nuclei, very efficient ice nuclei in small numbers into natural cirrus that are forming via homogeneous nucleation. And so the idea would be that you form a small number of ice crystals that grow quickly, sediment out, and suppress the natural cirrus. And by so doing, also you make the cirrus thinner, and then the ice sediments out, and so you dehydrate the upper troposphere as well. And it's not too dissimilar from this technique called intentional stratospheric dehydration, which I just read about. Where the suggestion is that you would inject heterogeneous ice nuclei into the air that's feeding into the stratosphere, and those ice crystals that would form would sediment out, lowering the water content, and so then you would supposedly then dehydrate the lower stratosphere as well. So the focus of the project is mostly on aging, and this is a slide just to remind us, and we all know this, is that aerosol undergoes a lot of aging in the atmosphere, and so it can undergo aging via deposition of sulfate or organics. It can undergo oxidative aging as well, but it can also undergo cloud processing, and so there is a suggestion from old literature, very old literature in the cloud physics world, that if you take for example, if you have a heterogeneous ice nucleus in a supercooled water cloud, and that supercooled water droplet freezes, and then the cloud evaporates and the ice sublimes, then you're still left with an ice nucleus, and there's a suggestion that those ice nuclei might be better than they were originally, because there's a bit of an imprinting of the structure of ice on the surface of that ice nucleus. And so we're hoping to look at all three of those types of aging processes. So just to remind, and everyone here knows this, just to remind everyone, the Cirrus are upper tropospheric clouds, much more prevalent in the tropics than in mid-latitudes, maybe 50% abundance, but maybe 25% abundance in mid-latitudes at times. And their temperature, which is relevant, is of course they're cold. Mid-latitudes, they tend to be most prevalent at around -50 Celsius or so. But in the tropics, of course, there's that more uplift associated, and so there's a mode that's quite a bit colder than that as well. So these are the major research questions we have. The first is to start with some porous particles and ask really how good are they as ice nuclei. And the motivation for this really comes from work that Zaman has done and others at ETH, where they have shown that porous particles can effectively nucleate ice. And so water can condense into these pores efficiently. Liquid water can condense into these pores efficiently below, via this inverse Kelvin effect, and then ice nucleation can occur in the pores, and then when you bring the relative humidity up above 100% relative humidity, then those ice crystals can grow significantly. And so we want to ask, for these synthetic particles that Zaman has been working with, how good are they, but also how good are they in comparison to other more natural deposition ice nuclei. Then we'll coat the particles after the meeting in November, and Frank Koich was talking quite a bit about diamonds, so we've added diamond into the system of synthetic particles that we'll look at, but then also try to coat with sulfuric acid and organics, and also look at some natural particles, which are the feldspars that we know are good ice nucleating particles. We can age them with OH, both the bare particles and also the coated particles. And the hypothesis there is you would think for the bare particles they may not do much, but in the lab, practically, it's very hard to form particles without some trace organic coatings on them. And so it's not impossible that the OH oxidation could actually sort of boil off those organic coatings, or they could take an organic coating that's not highly oxygenated and add a lot of oxygen to it and make it a better ice nucleus. And then with diamond, I don't know what happens. It is carbon, so you sort of wonder whether OH could do something to it. And then also look at this prior ice processing, ice cloud processing effect as well. So, so the way that we think about this and the community thinks about these processes is in terms of a plot with supersaturation, or relative humidity with respect to ice, is on the y-axis, temperatures on the x-axis. And the solid black line is the water saturation line. The blue solid line is the threshold for homogeneous freezing of aqueous droplets or sulfate droplets. And so the heterogeneous particles all act at lower, if they're good, they're acting at lower supersaturation ratios than the homogeneous freezing condition. And so the first set of experiments I just want to mention to you, we haven't yet attempted these yet, is to take porous particles and hold them below ice saturation for quite a long time so that the water can fill up those pores, and then to slowly bring the ice saturation up and to see whether we get freezing. And so the silica particles exist. These are being made by Dominik Burgweiler in Zurich. And so these are silica particles. Don't ask me how he does this. He's a materials chemist, and it's all a bit of a mystery to me. But he can make pores, and he can characterize their sizes, a few nanometers in size, and the surface area of these pores of these particles that stay the same size goes up by an order of magnitude or so. So these exist, and we can work with these now. And so the project, and Zaman previously has shown that they are good ice nuclei if the temperature is sufficiently low for these sort of few nanometer size porous particles. And so the experiments to probe them sensitively and as a function of time are going to be done at UNAM by Luis, who's sitting back here. And so this is with a microscope technique where the particles will be deposited onto a hydrophobic slide, and then held at a low temperature and a controlled relative humidity, and then interrogated with a microscope. And so the experiment exists. The first year has been spent, rebuilding the experiment. It was already existed to work at higher temperatures, but now this is to work down at these upper tropospheric temperatures, and hygrometers in place, and the system is going to be used over the summer for looking at this process. I'm going to spend most of my time talking about just more conventional nucleation in cloud chambers, where we very rapidly expose particles to this high elevated supersaturation. And so this is work that's going on both in Toronto and in Zurich. And the experiment is to generate a particle, size select a particle, and size becomes quite important, and then eventually interrogate it with an ice cloud chamber where we can control the supersaturation that we expose these particles to. This is all a continuous flow experiment. And then along the way, if we want to, we can coat them by exposing them to supersaturated vapors of organic or sulfuric acid. The organic will initially target both a liquid organic and a solid organic to sort of just probe the effective phase. And then we can also age the particles by exposing them for a short period of time to an incredibly high OH concentration, about 10 to the 9, 10 to the 10 molecules per cubic centimeter, by using 254 nanometer light, ozone, and water. And this is not highly representative chemistry of gas phase chemistry, but for heterogeneous oxidation of a surface where we know the OH concentration, we can, I think, reasonably describe the OH processing that goes on heterogeneously of the surfaces. And so the heart of the chamber is an ice cloud chamber. So these are home-built chambers. The design we're using is one that Zaman and I put together about 15 years ago, where we take two plates, take a warm plate and a cold plate, and a continuous flow chamber, and we coat the inner surfaces of each of those plates with ice. And so we know what those are the water vapor supply, so to speak. And then that sets up a linear temperature gradient between the plates and a linear partial pressure gradient between the plates. But because of the Clausius-Clapeyron equation, you get a supersaturation. Because of the nonlinearity of the vapor pressure with temperature, you get a supersaturation of water vapor in the center of the chamber. And so you inject particles right into the center of the chamber, and then you have sheath flows of clean air above and below where the particles are getting injected. And then you interrogate, you know how many particles you put into the chamber in the denominator, and then you measure how many ice crystals come out using an optical particle counter. And because of the size differences, you can differentiate between the particles that you put in and the ice crystals that come out. And the droplets you can ignore in that figure on the right, because we're going to work at so low temperatures that those droplets won't be forming. So yeah, I should say that we have these chambers both in Toronto and in Switzerland. But the ones in Switzerland have Swiss engineering, so they look a whole lot nicer than the ones in Toronto. So we used it to study feldspars. We were the first group to do this systematically quite a while ago, and they're very good, natural ice nuclei. And when you have worked in this field for a while, you sort of are surprised by sometimes what you wrote a while ago. And so, the last sentence of the paper was, on the other hand, if cloud seeding were to proceed under deposition mode conditions, for example, in the seeding of Cirrus clouds, it appears that feldspar minerals would be a good option. So I don't know why I wrote that, but it seems like they're a natural, good, heterogeneous deposition mode or pore freezing condensation mode ice nucleus. And since then, there's been a lot of work done on feldspars, and there's a nice paper in Science on which face of the feldspars is that which is nucleating ice. So we're starting with feldspars, and so I just want to give you a taste of how the data look. And so Carolina in Toronto has been, in the last couple of months, getting this experiment running well. And so the way that we plot the data is as an activated fraction of particles that you put into the chamber, how many of them form ice, as a function of supersaturation. And so for sulfuric acid, we know that they should freeze homogeneously, those particles. And so you see a very, very abrupt transition to ice at a specific relative humidity, and that matches up with the theoretical understanding of this process that was published quite a while ago by Koop et al. But what you see for a heterogeneous ice nucleus is a little bit different. So these are plagioclase. This is a type of feldspar. And so for the first 10 or 20% relative humidity, you don't see much happening. But then you see an increase in the ice nucleating efficiency of the particles, but a small fraction of them. And so the question is, how do you refer to an onset or not? And sometimes we just say, okay, let's pick a number, 10 to the minus 3 of the particles. At that level, then they are acting as ice nuclei at 130% relative humidity. But then most of them don't do that. They activate homogeneously, or in a homogeneous-like mode, where probably some water is condensed on the particles, and then that water layer freezes. And we could talk about that. And so there is a question about how you define what ice nucleation is for a heterogeneous ice nucleus. And so in Zurich, this is work that's been done by Kunfeng, who's here. He's been dry dispersing particles and also wet atomizing particles. He's been using two different types of potassium feldspar, referred to as Namibia and Elba. And then so he size selects, and then he takes them into the cloud chamber that exists at ETH. And so size selection is critical here, and it's interesting. This is a theme that's sort of coming up through the conference. Is what sizes do you have, and how do you generate them? And so the relevance here is that you can size select, and when we talk about monodispersed size selection in the lab, it's really a misnomer. We can't form individual sizes of particles the way that materials chemists can. But and so if you look at the 400 nanometer nominal particles, there are some that are up at 650 nanometers, and you know, a few percent of the particles maybe. And so that matters if the larger particles are better ice nuclei. And it'll matter a lot if this were ever implemented in the field. So these are the data that Kunfeng has generated, and they tell us a lot. And so this is all for, he's done this for 2 different types of potassium feldspar, and also for 2 different modes of atomization. And so these are Namibia dry dispersed particles, and he's done it as a function of temperature and as a function of size. And so at high temperatures, it's in the droplet mode freezing, where you hit the water saturation point earlier. And so those all occur at the homogeneous freezing temperature that you would expect, or conditions that you would expect. But it's at the lower temperatures that things get interesting. So for example, here at minus 45, you see that the biggest particles, 800 nanometer particles, show a mode of activation which is not nearly as prevalent for the smaller particles. And I'm not entirely sure I understand why this is the case, except they're just saying that the bigger particles have these sites on them and the smaller particles don't. I mean, you can see a hint of it in the 400 nanometer particles kicking in, and you know, maybe not in the 200 nanometer particles. So again, it brings up a question about, you know, what do you refer to as an onset for ice nucleation with particles of this type? But this efficient mode of activation that kicks in at low relative humidities with respect to ice gets more prevalent as you move to lower and lower temperatures. So that, you know, in this case, you know, at 218 Kelvin, for the largest particles, it seems that many of them are activating at that, or increasing numbers of them are activating at lower relative humidities. So, this is the summary of the data that Kunfeng has collected, and there are a lot of data points here, but just to contrast the large particles with the smaller particles tend to activate, and this is a criterion, I think, of 10 to the minus 3 activation threshold, more like a homogeneous type nucleation. So you would say they would not be very good at suppressing natural cirrus. But if you wanted to do that, you would choose, you would want to work at lower temperatures, of course, but also with larger particles. The atomized particles are in green. The dry dispersed particles don't have the green circle. And so the wet atomized particles seem to be less active. Maybe that's just an experimental artifact. It's very, very hard to not have organics present in our solutions. We've tried very hard to just atomize ammonium sulfate as clean as you can buy, absolutely baked glassware, clean water, and you always get organics in those particles. And so there could be an effect here that comes from the way that we do the atomization, but it could be that the particles are a little bit soluble too. And those solutes, when you wet atomize, are left on the particle after drying, covering up some of the active sites, which is not the case necessarily with the dry dispersed particles. So again, it sort of speaks to how you would prepare these particles for the field. And so this is really a summary of you know, much of what I've been talking about, that what's going to affect the ice activation onsets. It's going to depend, of course, on the particle composition. We can show you particles that are not effective heterogeneous ice nuclei. The mode of preparation, the temperature, the time at which the particles are exposed to these higher supersaturations, the degree of activation that you define as being where ice nucleation occurs. And that would have to be, you know, if you were to implement this in the atmosphere, you would have to take that full activation spectrum, I believe, and put it into a model to see how that would affect the nature of the cloud formation. And then also just what you define as being ice from an experimental perspective. So the last mode of experiment is what we're going to do in the last year of the project, and it's to probe the processes that occur after you have initiated ice formation, sublimed the ice away, and then reinvestigate the ice nucleation. And so we go down and then back up again. And so this will be an experiment done collectively in Zurich. So we'll take our oxidation flow reactor and our ice chamber to Zurich to couple up with Siemens. And so if we get this all to work, we'll take particles, we'll size select, And then if we want to, we can age them by coating them or oxidatively aging them. Then they can go through a cloud processing chamber. And Zaman has the ability then to sublime the ice at cold temperatures to get back to the original bare particle. And then we can send them again into an ice nucleation or ice cloud chamber. Okay, so I'm just going to finish up there. There are many uncertainties associated with Cirrus cloud seeding, and I've mentioned these: the dependence of the ice nucleation onset on particle type, size, preparation mode, atmospheric history, and each particle type has an array of onset efficiencies. I think that's important to recognize that there's not a single value, and what would be a challenge in the field? Inadvertent overseeding. So if you send in too many particles, ice nuclei, into a natural cirrus and just deepen the cirrus so that you don't form a lot of large ice crystals that sediment out. You would have to be able to forecast where the natural cirrus are. You'd have to be careful that you're not working with a cirrus that is already been seeded by heterogeneous ice nuclei. And Dan Sitso has a paper on this showing that a number of cirrus are heterogeneously nucleated. And then also, you don't want to, of course, seed in regions that are supersaturated but are cloud-free regions, like in a contrail type scenario, which would counteract what you're hoping to do. So with that, I'll stop.